Alright, what's up you guys? Today I'm going to do something that I've never done before on here, and that is I'm going to be reading from this book here, which I have not read to completion. What am I saying? So we've got differential geometry here. This is probably, if you read online, not the most hardcore book on differential geometry, but it's very accessible. It is still serious because it's very proof-based and there aren't very many mechanical questions, if you will, or just like where you're doing rote computations. It is very proof-intensive, but what it lacks in breadth of just differential geometry in general, it makes up for in focusing on things that are applicable to understanding theoretical physics, namely things like general relativity, which rely heavily on differential geometry. Some would say that differential geometry is like a language that general relativity is written in. But I am not a mathematician, okay? So let's just get that out of the way. But I want to, I read this Intro to Analysis book over many years, I guess, and reading math books is not like reading, Charles Dickens or Thomas Pynchon. It's kind of a thing where you could almost just read a definition or a theorem from and then just go about your life for a week and just kind of be tossing that theorem or whatever, that problem in your head that whole time, and maybe you figure it out, maybe you don't, and then you come back to the book, you read like a paragraph and you get to the next theorem, and then now you're going to think about that for another week kind of thing. So I wanted to film actually reading from this book, and so currently I'm on page 33, which is in the middle of, I guess you could say, section 11 of the first substantial chapter of this book. So I'm recording the screen right now and I'll hopefully splice this together, but I wanted to start off on a problem from an earlier section, from section 7, and then I'll get back to reading where I am now for you guys. So this is problem 7.1, and it says a one-to-one and continuous image, that is a topological image of a segment, is called a Jordan arc. And it says see section 6 for the exact definition, which I'm not going to do right now. One should perceive that the two conditions, one-to-one and continuous, are both necessary in order to exclude point sets which are two-dimensional. So the problem is prove, the first part of the problem, it's a two-part problem. First part is prove that the interval open at 0, closed at 1, and we'll call the interval variable t, can be mapped in a one-to-one manner onto the square, open at 1, closed at 1. We'll call this first dimension x1, where 1 is a subscript. Similarly, we'll have another interval for a second dimension. We'll call it x sub 2, open at 1, open at 0, closed at 1, of the x1, x2 plane. So I'll read that one more time. We're going to prove that the interval of t, open at 0, closed at 1, can be mapped in a one-to-one manner onto the square in an, we'll call it an x1, x2 plane that's open at 0 on both dimensions, closed at 1 on both dimensions. How about this? I'll jump over and I'll draw I'll draw what's going on here. So we have, call this t. We'll put 0 here. We'll put 1. And we're going to map this onto x1, x2, 1, 1. This is a hard boundary here. Got all this, like that. But key is that we're open at 0, and we want to come up with f. F is 1 to 1 and continuous. All right, now I'm going to jump back to the problem. So we basically want to come up with a mapping from T to the plane x1, x2, and we want to show that that mapping is 1 to 1 and continuous. Or actually, no, we're not worrying about continuous yet, just 1 to 1. So to make this fun, actually, I'm going to open up ChatGPT and I'm going to ask it this question myself. I already know what the answer is, which is it involves using the infinite decimal expansion of a real number on the interval of t. You make the mapping based upon the digits. You could do pretty much any mapping you want. You could like alternate the say like the even digits from the infinite decimal are mapping to the x1 coordinate, and then the even coordinates are mapping onto x2, or vice versa. Or you could do like 2 digits and then 1 and then 2 digits, and then like you can come up with different schemes, but it basically involves like using the indices of an infinite decimal from t to map onto x1, x2. But also you should realize from the picture here that the geometric configuration of the domain is a line, okay, right? The t input that we're putting into the function f is, you could say, one-dimensional, but the mapping is onto, you know, a square, obviously, which seems like a two-dimensional geometric configuration. And we're showing that this function f here that I kind of just outlined is 1 to 1. So it's kind of counterintuitive, if you will, that you could have a 1 to 1 mapping that does not preserve this geometric configuration, at least with respect to like the dimension of the spaces involved, it seems. And then I guess to jump ahead as well, the second part of the question, once you close the domain interval and the mapping, what you're mapping to, when you close and you allow the origin or 0 to be included, that we have enough that we can say that this function is continuous. Okay, so that's me as a human talking about it, right? But we're going to put this into ChatGPT here. Prove a from t1 to x2 probably from 2 has t in a manner which is 1 to 1. Alright, so this is my input. Prove that t open at 0, closed on 1 can be mapped onto x1, x2. Open at 1, or open at 0, closed at 1. This is a subset of the real line crossed with the real line. Anyways. Alright, so first of all, we have okay, it doesn't use the infinite decimal, but we'll say, okay, well, at least, spit some stuff out. But you know what I was talking about the geometric configuration not having its dimension preserved, or in other words, the geometric dimension is not invariant. Let's ask if ChatGPT can have this kind of geometric insight about the problem that, it just spit out a logical proof. I'm not going to double check it because, first of all, there are a couple problems. It's listing out injectivity, surjectivity, but then the sections aren't enumerated. It's just like one, like it's starting a list, and you would expect that surjectivity would be 2, but it's 1 again. But just at like a glance, we'll just say whatever, right? But I'm going to ask it about the geometric invariance of dimension. Was the geometric one mapping? So right here it says, yes, precisely. The proof demonstrates blah, blah, blah. Okay, next we have the interval, open at 0, closed at 1, is a one-dimensional space, as it can be represented by a single real number along a line segment. On the other hand, the interval, open at 0, closed at 1, squared, is a two-dimensional space. Okay, despite the difference... Okay, so it says all this stuff, and it seems kind of contradictory, okay? Because, I don't know about you, but just considering the problem, it's like, well, we have a line versus a square. Something's not right here. But then ChatGPT is saying, yes, precisely, this is preserved, but then immediately contradicts itself. So let's go back to the book here, and then we can actually go to the answer, which is one of the nice things about this book, is that it has all of the answers to the problems worked out in the back. But that's, this is not like you're doing, whatever kids use nowadays to get your calculus homework on time, but you don't understand calculus kind of thing. This is like, you need to see the answer, and then you'll read the proof, and you'll still be like, okay, there's still more to figure out here. So we'll go to the answers, and we can read this off here. Every number t between 0 and 1, including 1, can be uniquely represented by an infinite decimal. T equals 0, comma, C1, C2, ellipses, Cn, ellipses. That just means 0 point. C1 is the first number, integer in the infinite decimal representation, blah, blah, blah. And it says, for example, 1/8 is 0.125, which is equal to 0.124999 repeating. Okay, this is another thing. Infinite decimals, I'm just going to rant about this a little bit. And it kind of touches on the other book that I mentioned in the beginning, Introduction to Analysis. So we're thinking about the real number system, okay? What does that even mean? Like, I can draw these lines here, and we have different stuff going on each of these number lines. This first one here, we're going to call this natural numbers. So notice that there is no arrow extending or implying infinity off in this direction, because we're going to start that at 1. We don't even have 0. We started off at 1, and all up and down here we'll have, by Peano's 5 axioms of the natural numbers, We can get things like 1 + 1 = 2 and recursively climb the ladder way up, and so we have all these guys out here. Okay, so I'm not going to dive into that, obviously. Like I said, I'm not a real mathematician. This is just kind of a rant and going off on just freestyle and hoping, I don't know. We can add more structure to the natural numbers though, right? So you could subtract 1 from itself by defining subtraction to be the addition operation upon an element with what its additive inverse is in order to obtain, by that operation on those two elements, you get the additive identity, which is the element in the set that you can then use that operation of addition with any of those elements, and you get the same element at the end, not the additive identity but the other element. So you can do all these kinds of things and start to talk about negative numbers and stuff, but we still only have whole numbers: 0, positive, and negative. Integers, calling them z. You could add more onto this by adding another operation, multiplication, which kind of implies, along the same talk about inverses with respect to that particular operation, and also an identity, a multiplicative identity, etc. You can get division, I guess, out of that and start making quotients of these integers per se. But we still haven't really gotten to real numbers yet, right? Like, this problem talks about infinite decimals, and I don't know if you've seen online people who are these cheeky, oh, I'm so smart, whatever. They'll be like, oh, I could write a mathematical proof that 0.999 infinite equals 1, which is correct, but they just kind of show it's something involving the notation, or it's just like a computation where you're symbolically rearranging these numbers and stuff, and so people don't really understand what's going on with this, right? To really understand, you have to be super rigorous about what you mean by a real number, right? So I'm showing you these things: natural numbers, integers. I just kind of talked about making quotients of numbers, so I didn't draw that out here, but we'll write that out here. Q, quotients, so that's z over z kind of things. You can even talk about square roots and stuff like that, but to cut to where this is going, you could really define and nail down the real number system with 3 broad properties. The first one is that the real number system is a field, and that basically means all of those things about having an addition operation, a multiplication operation. You have the existence of inverses on all the elements in the real number set that can be operated on with each of these operations. So elements, inverses, you have the identity elements. You get all these algebraic properties. Once you throw in parentheses, basically, can you swap elements around within parentheses? If you have multiplication on the outside, how does that distribute over the things on the inside of the parentheses? That's all good. That's the first property. So those you would call the algebraic properties of the real number system, okay? That doesn't have to do with the whole infinite decimal cheeky 0.9999 equals 1 stuff. I'm getting there. The second property of the real number system is order. So it's basically kind of like how you could say on the real or on the natural numbers, you have 1, 2, 3, 4, and all of those are in an ascending order. So 2 is greater than 1, 3 is greater than 2. There's an order to these elements. You could say, to give it more context, like a field with all of those algebraic properties, that's a lot of properties, you could dull it down to just one operation and not have as many strict requirements, you could say. And it's not called a field anymore, but it's called a group. But it's still a group and a field, though, are both mathematical structures upon a set. So my favorite example, of course, is that the set of all Rubik's Cube permutations is a group. You could say the operation is turning a single side, and all of the different permutations, you know, can be related to each other by applying the operation of turning a side you can get from any one of the different permutations to another. But there isn't the kind of order on the Rubik's Cube group of like greater or less than as there is with natural numbers or integers or real numbers. But suffice to say is all of those extra algebraic structural properties of, you know, a field that the real number system has, you can still have this kind of order of greater than, less than, ascending, descending, that, you know, is also present in like natural numbers. But furthermore, if you have the complex number system, or if you compose a real number with the imaginary component, we're not going to get into this now, obviously, in depth, but there is not an order on the complex number system, but there is on the real number system. That also doesn't have to do with the infinite decimal stuff, though. The third major property of the real number system, which really this is all coming down to, is the least upper bound property of the real number system, which is... Alright, we're recording again. Anyways, as I was saying, if you have any set of real numbers, okay, if that set is bounded above, then you have a least upper bound. You could come up with a bunch of upper bounds for a set of real numbers that's bounded above, but there's a minimum, a least upper bound of that bounded above set of real numbers. That is really the key to the whole 0.99999 equals 1 thing. It's basically that the least upper bound of a set, let's say being 1. So you could have a set of real numbers, let's say it's bounded above by 1. The number 1 doesn't have to be included in that set, but 1 is still a least upper bound of that set. So we could return back to the original problem here, where we've got 0, whoops, oh shoot, alright, fuck, 0, and you have 1, and this is 0, 1 is the way you could write this. This is T. Okay. So you could even flip the least upper bound property, and you could say it's a maximum lower bound, but that's kind of, that the way that that's phrased kind of betrays the important meaning of this property, okay? So, but you could say if there's a set here where 0 is the upper bound of the set, so you could even just do this right here. 0 is an upper bound of this set. Or you could say that 1 is also an upper bound set. You could say 100 is, or 106, as I just wrote, perhaps even. That's also an upper bound of this original set. Negative infinity is 0. The thing is that 0 is the least upper bound of this set. And it's saying that, like, let me put it in a different way. You could define an interval like this, 1/2, and you could include it, but this is a this is a subset of integers here, then even though the way you've defined this set, the technical upper bound of it is 1/2, and it's included in the set by the fact of saying it's a subset of the integers, this upper bound is not included in the set. Like this 1/2 is not a point within the set. It's just a boundary that kind of lets you define the scope of this set, if you will. The least upper bound in integers of this set would be, I think, what, 0? Yeah, 0. So that, anyways, so a property of the real numbers though is that, you know, had this been not Z but it's R, and if it were open instead of closed, then 1/2 is in this set. The notation is probably confusing the hell out of people, but I just, you know, I'm just freestyling this video, honestly. But that's what I have to say about this problem. Well, but even if you go further, it even says right here, our problem illustrates the fact that the dimension of a geometric configuration is not necessarily invariant with respect to one-to-one mappings. The discovery of this fact by George Cantor in 1873, Cantor had far-reaching consequences for the development of geometry. So that, you know, these are the kinds of things that you can plug into ChatGPT to expose. I wouldn't really call it a hallucination, but, you know, for all of the glitz and glam of these large language models, there's clearly a deficiency in the geometric, mathematical reasoning capabilities of ChatGPT. And if you know about mathematics, you can pick apart these kinds of things. This is just an example, okay? Anyways, that's a long rant that I started. I was originally going to just read a section to kind of take you guys along with what it's like for me to read stuff that I'm not totally familiar with. But my laptop is burning up, surely, making this file. So I'm going to cut it here. See you guys in the next one.